Hello and welcome to the world of astronomy. This is Akashvir and you are watching The Fact Sci Guy. Today I will discuss about antimatter. Have you ever thought about antimatter? Antimatter has inspired science fiction stories, but these fascinating facts show that it is not just reserved for fantasy. In the books Angels and Demons, Professor Langdon tries to save Vatican City from an antimatter bomb. And in Star Trek, the collision of matter and antimatter supplies energy to propel the starship Enterprise to faster than speed of light. But matter and antimatter is not just the stuff of science fiction. While these scenarios are far-fetched, these are still many facts about antimatter that will tickle your brain cells. I will tell you about 10 important and amazing facts related to antimatter. Point number 1. Antimatter should have annihilated all the matter in the universe. Antimatter particles are almost identical to their matter counterparts, except that they carry opposite charge and spin. Matter and antimatter particles are produced as a pair, and when they meet, they immediately annihilate each other, leaving nothing behind but energy. This means that the Big Bang should have created and destroyed equal amounts of these particles. So, why do we exist in a universe made almost entirely of matter? As far as physicists can tell, it is because in the end there was one extra matter particle for every billion matter-antimatter pair. Physicists are hard at work trying to explain this asymmetry. Point number 2. Antimatter is closer than you think. Small amounts of antimatter constantly rain down on the Earth in the form of cosmic rays, energetic particles from space. These antimatter particles reach our atmosphere at the rate of ranging from fewer than 1 per square kilometer per country to more than 10,000 per square meter per second. Scientists have also been and seen the evidences of antimatter production in both thunderstorms. But other antimatter sources are even closer to home. For example, banana radiate one positron, the antimatter equivalent of an electron, roughly every 75 minutes. This occurs because banana contain a small amount of potassium-40, a naturally occurring isotope of potassium. As potassium-40 decays, it occasionally splits out a positron in the process. Our bodies also contain potassium-40, which means positrons are being emitted from us. Antimatter is annihilated immediately on contact with matter, so these antimatter particles are very short-lived. Point number 3. Humans have created a tiny amount of antimatter. Matter-antimatter annihilation have the potential to release a huge amount of energy. A gram of antimatter could produce an explosion the size of a nuclear bomb. Scientists create antimatter to study in experiments, but the amount produced is minute. All the antiprotons created at Fermilab Tevatron particle accelerator add up to only 15 nanograms, and CERNs so far add up to about 1 nanogram. The problem lies in the efficiency and cost of antimatter production and storage. Making 1 gram of antimatter would require approximately 25 million billion kilowatt hours of energy, and the cost over $1 million billion US. Point number 4. There is such as an antimatter trap. To study antimatter, you must prevent it from being annihilated by matter. Scientists do this by holding the charged particles such as positron and antipositron in devices called penning traps. These traps are comparable to tiny accelerators. Inside, particles spiral around as magnetic and electric fields keep them from colliding with the walls of the trap. But penning trap won't work on natural and neutral particles such as antihydrogen, because they have no electric charge, and these particles cannot be confined by electric fields. Instead, they are held in loft traps, which take advantage of the particles' magnetic properties. Loft trap works by creating a region of space where the magnetic field becomes larger in all directions. The particles is scattered to the area with weakest magnetic field. It was like how a particle and how a marble rolling around a ball eventually reaches the bottom. Point number 5. Antimatter might wallop. Antimatter and matter particles have the same mass but different in properties such as electric charge and spin. The standard model as the theory that best describes particles and their antiparticles interactions, predicts that gravity should have the same effect on matter and antimatter. However, this has yet to be seen. Experiments at CERN such as AEGIS, ALPHA and G-bars are trying to find out. Observing gravity's effect on antimatter is not quite as easy as watching an apple falling from a tree. These experiments need to hold antimatter in a trap or slow it down by cooling it to temperatures just above absolute zero. And because gravity is the weakest of the fundamental forces, physicists must use uncharged antimatter particles in these experiments to prevent interference from more powerful electrical forces. Point number 6. Antimatter is studied in particles accelerators. You have heard of particle accelerators, but did you know there are also particle decelerators? CERN houses a machine called the antiproton decelerator, a storage ring that can capture and slow antiprotons to study their properties and behavior. In circular particle accelerators like the Large Hadron Collider, particles get a kick of energy each time they complete a rotation. Decelerators works in inverse. Instead of an energy boost, particles get a kick backward to slow their speeds. Point number 7. Neutrons might be their own antiparticles. A matter particle and its antiparticle partner carry opposite charges, making them easy to distinguish. Neutrinos, nearly massless particles that rarely interact with matter, have no charge. Scientists believe that they may be majorana particles, a hypothetical class of particles that are their own antiparticles. To determine whether this is the case, scientists are looking for a behavior called neutrinoless double beta decay. Some radioactive nuclei simultaneously decay, releasing 2 electrons and 2 neutrinos. If neutrinos were their own antiparticles, they would annihilate each other in the aftermath of the double decay, and scientists would observe only electrons. Finding majorana neutrinos could help explain why matter-antimatter asymmetry exists. Physicists hypothesize that majorana neutrinos can be either heavy or light. The light ones exist today, and the heavy ones would have existed only right after the Big Bang. These heavy majorana neutrinos would have decayed asymmetrically, leading to the tiny matters exist that allowed our universe to exist. Point number 8. Antimatter is used in medicine. Positron emission tomography uses positron to produce high-resolution images of the body. Positron emitting Radioactive isotopes, like the ones found in bananas, are attached to the chemical substances such as glucose that are used naturally by body. These compounds are injected into the bloodstream where they are naturally broken down, releasing positrons that would meet electrons in the body. These particles annihilate each other, producing gamma rays that are used to construct images. Physicians can already target tumors with precise beam of positrons that release their energy only after safely passing through healthy tissues. The scientists working on CERN's antiproton cell experiment studied the effectiveness and suitability of using antiprotons instead, which adds on an extra burst of energy. The technique was found to be effective in homestar cells, but some researchers have yet to conduct electricity studies, magnetism in human cells. Point number 9. Leftover antimatter might still be lurking in space. To solve the antimatter and matter symmetry problem, scientists are looking for antimatter leftover from the Big Bang. They says that these particles used in alpha magnetic spectrometer, a particle detector on top of the International Space Station. The AMS alpha magnetic spectrometer contains magnetic fields that bend the path of cosmic particles to separate matter from antimatter. Its detectors assess and identify the particles as they pass through. Point number 10. Antimatter could fuel spacecraft. This is one of the most important data in relation. Just a handful of antimatter could produce a large amount of power, making it a popular fuel for futuristic vehicles in science fiction. Antimatter rocket propulsion is hypothetically possible, but there is currently no technology available to mass production or collect antimatter in the volume needed. One day, if we can figure out a way to collect enough antimatter propelled interstellar travel could have a reality. Thank you very much for watching. If you like this video, please like, share and comment. And if you want such videos, please write in the comments below. Thank you very much. Have a good day. Take care.